Cool. So off the back of that, we are now going to talk about pointers, references, constness, and virtual function tables. First off, we're going to talk about pointers and references. So we used a little bit of pointers and references in the examples before when we were getting the memory address of things. So unsurprisingly, everything in memory has an address. We saw this in the previous workshop. A pointer is just an address, and since addresses are 64 bits on a 64-bit machine, this means a pointer is just a 64-bit integer under the hood. It's obviously faster to pass a 64-bit integer through the call stack when you're calling functions than copying the whole object. You can also store pointers inside objects on the heap because, again, they're just pointers inside objects on the heap that you've allocated. And then, yeah, if you don't, if you no longer have a pointer to a heap memory that you previously allocated, like you forgot to call delete and you don't have any pointers to that allocation anymore, then it's a memory leak because you can never call delete on it, and it's just that memory is just gonna stay used until your program exits. Memory leaks are bad. So what is a reference? So bear with me. Pointers are kind of awkward because the code has to deal with the memory address instead of just like the actual thing you want to use, just to avoid copies, right? And then every time you want to get at the object data, you have to like dereference it, right? Either with the leading star or with the arrow to access the member of a thing that is being pointed to. Pointers can easily be null. You can set them to null pointer, and then you've got code that has to check for null constantly, right? Because these things could be null. And really, in a lot of cases, we just kind of want to avoid copies. We just don't want to be copying when we call into every single function. So a reference is it implicitly refers to another memory location. So it's invisible to the consuming code. You'll know that it's a reference from the AND symbol on the type, but the code that's consuming it can just treat it as if it's a local value. This code here, it does what you expect. It prints 10. So in this case, what we do is we create an integer on the stack, A, we set it to 5. We then create a reference to A, right, called B, and then we set B to 10, which is really setting A to 10, right, because B is just a reference to A. And then we print B, and it prints 10, right? But notice the code didn't have to like dereference anything. It just could just assign to B, and it did what you expect. And so the way I like to think of things is like references are like implicit memory addresses, right? So you've got it's invisible, it looks like a local variable or your parameter, and then your pointers are your explicit memory addresses. So this is where you actually see the actual pointer. You see that there is a memory address involved. If you want to take the memory address of something so you can assign it to a pointer, you need to use the address of operator, which is also the AND symbol. And then to actually get at the value, instead of just dealing with the pointer, if you want to deal with the things inside it, we have to dereference B. And in this case, when we dereference B, we're actually going to get an int reference back, right? We're not getting an int back because if we got an int back, we'd be working on a copy, right? We're getting an int reference back. That will basically be pointing to A. With pointers, you can set them to null pointer, you can point them anywhere, you can do whatever you want. Pointers, you are dealing with a memory address first and foremost. Yeah, it's fairly straightforward. You can reassign pointers to point at anything. Like before, when we were moving things around, we can add numbers to them, and it'll move the pointer by the size of the type that is being pointed to. In this case, on the code on the right here, this prints 10 because it just happens that the C local variable is sitting right after A in the stack, right? Because when we've allocated our stack memory and we've put our 5 and we put our 10, and then we happen to take the address of where 5 is, we're taking the address of the A, and then we're moving it down, we're moving it through the memory by 1 or by size of int because of how pointer math works. And then we just read out 10, and it's like, sure. You can just set them to wherever you want. This is like totally fine, but it will obviously crash because this memory address isn't a thing that you actually own. But But you can just put whatever you want. It's just a 60, like a pointer is just a 64-bit number. You can put whatever you want in there and then dereference it, and then your program will crash. But yeah, I really want to stress the point is just put whatever you want. Type operator comparisons. Oh lordy. Oh right. Okay. So this is just if we're comparing. We're just comparing like again. We're just comparing like references versus pointers, right? And how you access members in them. So if we have an ftest class on the stack, we just access the members through the dot operator, right? Which is just access the member, right? If we take a reference, if we have a reference to a thing, whether it's on the stack or heap, again, we just use the dot operator because we're just accessing. It's invisible, right? The reference is effectively invisible to the consuming code. If it's a pointer, then we actually need to deal with the fact the pointer is present. So we need to use the arrow indicator to access the member instead of seeing the pointer itself. Or you can also do, like I said before, you can also dereference the actual pointer to get the reference to the thing and then just access it normally. Where to use them, or when to use them, sorry. References. Function parameters, when we want to avoid copies, that we can use const reference, which basically means you can't change the thing that's being referenced. If we want to do out parameters, right, if you're used to out parameters or ref parameters in C#, you can just use a reference. And then like earlier when we were assigning 10 to B and having it change A, if you have a ref, or if you just have a reference as a parameter in C++, it gives you the same thing, right? You can assign or modify the data inside the function and it will be reflected in the parent. Use references when the thing should not be null, when the code doesn't need to modify when the reference points to, if you use a const reference, when the code doesn't need to get the address of the target object or it doesn't want to be dealing with the address constantly. You could still technically get it by using the address of operator, but you know, when you want to deal with something as if it was local, reference is a good option. Pointers, typically members inside classes or structs that have memory addresses of other objects, will be a pointer, not a reference. You're not really going to use references as fields inside classes or structs. You can, but it's fairly complicated. We're not going to go into it. So you're going to use pointers there. You can set it to null pointer. You can set it to any address you want. If you're referring to raw blocks of memory or things you've created with new, they're going to be pointers because that's just how language works. You need to have a pointer to point at the memory, right? You can obviously then pass that memory as a reference down to things by using a dereference operator, but you have to have the pointer itself because that's what's pointing to the heap, and that's where you can, and that's also, the pointer is also the thing that you're going to call like delete on to free the memory later. Pointer to a pointer. So if we have T star star, this does mostly what you should expect. It is a pointer, so 8 bytes on the stack. That is a pointer. It's a pointer to a pointer. So then you're going to have 8 bytes in the heap that then is also a memory that also contains a memory address that then points to the actual thing. Somebody in chat just says, I think this is why 32-bit operating systems can only use 4 gigabytes memory max. And you are correct, because the addresses in a 32-bit program or 32-bit operating system is only 32 bits wide, so you could only address 4 gigabytes of memory maximum. That's why you have to have 64 bits if you want to address more memory than that. So the example of the memory, so that sort of gives you layout, like, hopefully that makes sense. You've got a pointer on the stack, it's pointing to the address of the pointer, and this is not really used that often. You don't really see it that often, but you might see it around the place. R value references. So you might have noticed these before in the move constructors. And I just want to be really clear that when I first was researching what this actually meant, my initial expectation, having done C++ for like 5 years, was wrong. And when I looked this up, I was like, oh, it's something completely different. So don't stress if you don't understand. Understand, it's totally fine. The R value references, which is like the and operator with regard to like types, it is a reference that is restricted to temporaries and constants, right? So it's basically used for move constructors and move assignment operators, and it's used to basically say, okay, temporaries and constants are things where it's safe to move from by default, right? Because if we look at the example on the right, where we've got like, where we'll say we're initializing like an F class, or we're calling a function that returns an F class. In this case, it's safe to use the move operator there because nothing else could possibly reference the F class, right? We've initialized it and passed it straight into parameter. Nothing else references it. So it's safe to steal resources from because nothing else could possibly be using it. So R value references are just a way of constraining a reference in the sense that it is safe to move from, right? And so like, for example, if the second example that's there, if we have an F class on the stack, and then we try and pass that into a function or a move constructor, it'll be like, no, you can't do that, right? Because other things could still be referencing val, right? There's a possibility that something else is referencing val. You can use stdmove or movetemp as an escape hatch to basically say, I really promise that I'm not going to use val after this point, so it's safe for you to steal the resources out of it. Of course, C++, you know, will totally let you still access it, and it'll just be garbage. I'm just gonna put this link in real quick in the chat so you can have a good look at some code. Help, I don't understand move semantics and R value references in June. What are you even talking about? Don't panic. It's okay. This is all fairly advanced stuff. Move semantics and R value references are optimizations to avoid expensive copies of large objects that are being passed around by value, like I was talking about earlier. It's extremely unlikely that you will need to deal with this in game code, but I cover it for completeness so that you don't, when you're looking at a move constructor, maybe you're looking at the engine code and you see this class has this really funny looking constructor, and you're like, what is that? What does the and mean? You will know what it means. It means it's a move constructor. And so, yeah, I cover for completeness. Cool. That's pointers and references. Let's talk about Constness. So const, aka read-only, you can make anything const in C++. You can make variable parameter types const. This makes the type read-only. You can make template parameters read-only. So if you have an array of, you know, const strings, it'll make it so that you can have an array of const objects. And you can have functions in classes and structs declared const. And what this means is that you're allowed to call this function even if you have a const like type reference to it, right? So if you've got a const f string, you can call any of the functions that are declared on f string if they're declared const. You can't call any ones that are not declared const because they might modify the f string, right? But any function that's declared on like f string that's const, you can call that on a const f string. And so basically const is for correctness, right? There's no inherent optimization benefits in using const, but it does allow us to make the use of references safer, which is what we will want to be doing to avoid copies. So here's some examples. We have our f class. We've declared that there's just a function. It's called mutating call. Notice we haven't. It looks like a normal function really. And then we've got a const call function that has this special const keyword at the end of it. I was going to say, and so on a normal pointer to just a normal mutable f class, we can call either of these functions. It's totally fine. But if we have a pointer to a const f class, then we can't call this mutating call because it might change what the class or the data inside the class, right? But we call it const call, the const function, just perfectly fine. Const examples, right? So these are various examples on how the const modifies the type depending on where it is. So the top example, we have a pointer to an f class. You can change the f class and you can change the pointer, what the pointer points to. If we have a const f class pointer, it means you can't change the f class is const, but you can set the pointer to something else, right? I could change the pointer to point at a different const f class. If we have an f class pointer const, this is fairly rare, we don't super see this, but if an f class pointer const, it means you can't change what the pointer points to, but you can change the f class that is being pointed to, right? And then if you have a const f class pointer const, It means you can't change either of them. You can't change what the F class is, or you can't change anything inside the F class, and you also can't change what the pointer points to. For references, same const semantics as the pointers, right? You can have a reference, or you can have a reference to a const F class. You can't have const references because you can't change what a reference points to afterwards, right? Once you make a reference, right? Once we've got that P equals A, we can't change what P points to. It is a reference and it stays a reference to the thing that it was initialized as. So therefore, there's no equivalent to the const pointer in references because you can't. They're already const, right? You can't change what they point to. All right, more code for everyone. Right. So passing by const reference. So now we've got references we talked about earlier, and we've got const, right? This means we can now eliminate copying when we call functions and save on both CPU and memory copies, right? If we look at this function which copies on call, it just takes an F class A. This has the semantic of when you pass an F class into this function call, it will make a copy of that instance because the function is going to operate on a copy, right? And you can see we've got all those move instructions there that are all about allocating enough space for the copy and doing all the copying that is relevant. Oh, so the doing the copy that's relevant is probably actually the orange that you see lower down right before the function is called. If we compare that with the function which does not copy, it just takes a reference, then the only thing we're actually passing is the memory address of F class. So when func which does not copy gets called, what it's actually getting passed under the hood at the machine level is it's getting passed the address of A that is on the stack, right, inside main. The address of A in main inside the stack, that is what gets passed in. And then from the code perspective, the reference is invisible. So you're just working with A as if it's just like a local variable. But actually, under the hood, there is this reference that's pointing to another location. Note that there's no benefit to passing things by reference if it's the same size as the memory address, because it'll fit in the same size when it's copied. So if we're passing, so in this case, we've got an F class, right? And it has a single 64-bit integer in it. Well, a memory address is just a 64-bit integer, right? So there's no difference, right, in terms of how much memory is being copied, because in both cases, it's just a 64-bit integer, right? So there's no benefit. If the thing you're passing is a long or an int or is the same or smaller than the size of a memory address, then there's no benefit to passing it by reference. And this is why you'll see that, like, in functions, doubles and longs and ints, they're never passed by, well, they might be passed by reference if you want to use them as an out parameter, right? If you want to assign to them and have them actually change, but you're never going to pass them by const reference because there's no point. It's going to be the same instruction count either way. I'll get to this link. Cool. On to virtual function tables. So this is a bit of a divergence from what we were just talking about. But what we're going to do now is we're going to look at how overrides really work under the hood, right? Like if you think about virtual functions in C# and C++, like how is it that you can call the correct implementation if all you're ever dealing with is like the base type? If you think about it for a moment, right? We've got this derived class that is inheriting from base class. It overrides A, and then code that has a base class pointer. How does it know, like actually in the code that's being executed, in the runtime execution, which A to call, right? C++ is compiled ahead of time. It can't do dynamic lookups or anything like that. So how does it actually work? Let's think about how we would implement it, right? If we wanted to have a function that we could change the address of, right? Or we wanted to have a class where we had a function and we could change what the implementation looked like. And we were not going to use any virtual functions, right? We're going to pretend virtual functions don't exist. So we could make a struct or a class that holds a function pointer. Now, remember earlier I said everything is just blocks of memory? Well, when the operating system loads your application, it loads your executable file and all the DLLs, they go into memory. And so all of the functions that you write, all of this, code over here that we've got, this all has memory addresses, right? when it gets loaded in by the operating system. Which means we can make pointers to those functions. And then what we can do is we can change those pointers. I'm just going to close one of these tabs that's making a bunch of noise at me, wherever it's gone. Excuse me. Bye. So we can change we can change what that pointer points to, what function that pointer points to. So in our base class, we can have our re-implementation of a virtual function table, which is just a pointer to the A implementation. And then in our base class, we set up this virtual function table to have the address of the base class implementation that we want the base class to have by default, which is going to be this base class A internal, right? We're taking the address of that function and we're putting it into the virtual function table. And then when derived classes get constructed, they just change what the function pointer points to, right? They also initialize the virtual function table, but we set it to a different address. And then when we use the code, what we do is we get the virtual function table, we say, give us the pointer that's going to hold the address of A, and then we're going to call the function using that pointer. And so then with the code on the right, it's now looking up the virtual function table in the actual instance, right, that we're pointing to, and calling the correct function that way. Hopefully this makes sense on some level. So what's the difference between what we just kind of did then as like a little re-implementation and what a real virtual function table implementation generated by the compiler looks like? In our case, we just like initialize the VFT in the constructor, but for the compiler, it knows where all the functions are going to be located. It can just like generate the whole VFT at compile time and just store it in the build executable. It doesn't have to like actually put it together in the constructor. In our case, we also stored the whole virtual function table inline in the class. But what you'll see when we get into Godbolt in a second is that we just actually store, in the real implementation, we actually just store the pointer to the virtual function table. And this is important because you can imagine, like, say we have a class with like 20 virtual functions, right? If we store the virtual function table in the class itself, that means every single instance of that class is going to have 20 pointers just for the functions, which are in almost all cases going to be exactly the same, right? Like they're just going to be the same every time. You just copy it every time. So that's just a waste of memory. So that's why we do a pointer to the virtual function table. That means, every single instance of the same class has the same pointer to the same virtual function table, and you're not wasting memory that way. Let's go to Godbolt. We're down to actual. We don't have that much more to go, so that's good. Right. Okay. Is this the right one? I think it is. Okay, cool. Excellent. So move my notes over there. All right, cool. So what we'll notice is that in the constructor for base class, you will notice that it is getting the address of the vtable, right, that it is generating, and this is located down here. The compiler is outputting this for us. And you'll notice that it has these function addresses are in this virtual function table. It is going to store the pointer to the virtual function table into this class, right? And then when the override class calls its constructor, you'll notice that it is setting its virtual function table into the same location. We'll get to where the virtual function table is stored, where the pointer actually is in a moment. And this is what allows us to do that sort of like on the fly, like lookup of where the function implementation actually is. Go down to here. This is a bit unreadable, but this is basically just a bunch of instructions that is looking up that virtual function table and then doing the call. See how this call is calling from a register? This register happens to have the memory address of the function we're calling, and all of these move instructions are just getting that address from that virtual function table so that we can call it dynamically. Okay, so where is the virtual function table pointer stored? If you have a class that has any virtual functions at all, then the very first thing in memory for that class is the virtual function table pointer. You will notice, remember before when we were getting the address of the first field inside a class, and it was the same memory address, and now it isn't the same memory address? That's because the first 8 bytes here is the pointer to the virtual function table, right? Depending on what the actual implementation of the class is either going to point to one of these virtual function tables. And then that way, that's where we're actually storing the virtual function table for all of these instances, so that when you access instance, right, when the code accesses the instance, it's like, okay, I got to call A. What it's going to do is it's going to go, okay, I know that the virtual function table is at the start of the class, because it's always at the start of this pointer. I'm going to look up, I know that A in base class is the first function, right? It's going to be like the third entry. In this case, it's like the third entry in the virtual function table. I know what index it sits at. I can just resolve the pointer, look at the third entry, and call it with the parameters, knowing that it's going to work. Hopefully this makes sense. This is not super critical to understand. I will say this is not super critical to understand how virtual functions work under the hood, but it is interesting to know how it works under the hood, because again, when I say everything is a block of memory, it means that the virtual functions, the way the virtual functions are looked up and called, everything's a block of memory. Virtual functions have to work within those constraints, right? Right. Okay. Right. This is also, if you've ever heard this thing where like it's okay, virtual functions are slower. This is why they are slower, right? If you call a function that is not virtual, right, the compiler knows where the address is, right? It's always the same memory address. You can just emit the call and you can jump straight into the non-virtual function. But if you use virtual functions, now you have to actually, at runtime, it has to actually go and get the virtual function pointer that's sitting at the start of the class that you're calling on. It has to resolve that pointer and look up the function offset inside the virtual function table, and then actually call the address, right? So you've got this intermediate step, and that's why virtual functions are slower. Not that much slower, but it can be noticeable in like performance critical code when you're iterating over lots of data, right? So that's something to keep in mind when you're using virtual functions, is they're slower because you've got this level of indirection. All right, this is going to get real complicated. Bear with me. So C++ doesn't have interfaces as a first class type, right? Interfaces in C++ are just pure virtual classes. If we want to do interfaces, we have to inherit from multiple classes. Each base class has its own virtual function table. So when we cast to an interface, right? Imagine we're inheriting from, I've got an example problem coming right up. How does the calling code know where the offset of the virtual function table is? Just got added. All right, I'm gonna ignore that. Right, so let's have a look at this example. So we've got base A. We've got two base classes here. We've got base A, base B. I'm gonna quickly flick this into. Base A and base B, right? So we've got these two base classes, base A, base B. They both have a virtual function A and B, and then we've got this derived class that inherits from both of them. You won't see this in C# because C# doesn't let you inherit from multiple classes. It does let you inherit from a class and multiple interfaces, which is basically the same thing, but you won't see multiple class inheritance. Now, think about this problem, right? Remember before, we just established that the virtual function table is always at the start of the class, right? So where do we put the virtual function table for base B? It can't be at the start of the class, right? Because, well, that's where the virtual function table for base A is, right? So if we create a derived, right, we put it in a base B pointer, how can the code that's calling it possibly know where the virtual function table is? It doesn't know that it's working with something that is actually derived. If we offset the virtual function table inside derived and we don't do anything special, it's not going to know where it is. And keep in mind that the code at the bottom there where we're actually invoking B, it has to work with base B. It has to work with things that only inherit from base B. It has to work with things that inherit from 20 classes and base B, right? How can it work? Here's the trick, right? We change the pointer when we cast, or we change the memory address when we cast. So if we look at the memory layout of derived, the memory layout of derived looks like this. It has the virtual function table for base A. It then has the fields for base A, because remember, if you're inheriting from a class, you get all the fields that are inside it. You then have the virtual function table pointer for base B, all the fields for B. And then if we had specified any fields in derived, we would have those specific fields after that, right? So that's what the memory layout looks like. And when we adjust the returned, when we cast from derived pointer to the base B pointer, we adjust the return pointer by the size of base A, so that the code that is using B in our little example here, it is actually not the same memory address that derived sits at. It's actually, in this case, it's 16 bytes, so x10. It's 16 bytes offset from where the derived pointer is. And what this means is that the code that then uses B, it accesses the virtual function table at the 0th offset, or like it accesses the fields with the, in this case, an offset of 8 bytes, and it all just works because from the codes, from the perspective of the code that's using B, it is just a pointer to a base B, right? In memory, it looks like, if you just look at that memory block, it just looks like a base B. Even though there's extra memory before it and memory after it, it doesn't matter. The code that's calling on base B just sees this base B, right? And then because the compiler knows that, derived inherits from base A and base B, then when you do the reverse, if you were to cast from a base B pointer back to derived, it knows that it has to subtract 16 bytes because it knows that actually there's all this base A data sitting before this base B data, and the derived actually starts earlier. I want to stress that's very much deep dive. How does it work under the hood? You don't need to know that level of detail to write C++ code, but it can be valuable to know how that works. And the code that I linked in, which I'm gonna probably not go too far in, this code demonstrates how you can see these pointers change when you cast to base B, right? You can see it's offset by those 16 bytes, and then when you cast it back, it subtracts back the other way. You can have a look at this code or ask me questions what all of this assembly means after I finished the session. Okay, so super important summary slide. Make sure you understand pointers and references work. You're going to be using them a lot. If you're using actors or UObjects at all, that's all pointers. You need to know how they work. You can use const references to pass things into function parameters if they're larger than a memory address, and that will save you instructions. It'll save you memory because you're not going to be copying all the time. You don't need to do it for things that are in long bool, anything that's smaller than a memory address, because there's no there's no benefit to doing that. And it's helpful to know how virtual functions work under the hood, so you know what the memory layout of things looks like, right? So if I'm making derived, it inherits from base A and base B, and they have virtual functions and I've got fields, then I can conceptualize in my head, when I allocate a derived on the stack or the heap, I know how big it's going to be because I've got those virtual function pointers and all the fields. I know what the layout's going to look like. And so it can help you get into that mindset of everything as a block of memory. But as I said, not critical for writing C++. If that kind of went over your head, totally fine. All right, that is the end of this session. So I will try and make sense of all of the little windows that I've got open wherever StreamYard's gone. And I will take questions now. I know we're running out of time, but I'll do it anyway.
Yeah, no problem. Thank you, June. No, this has been really great. Yeah, if anyone's got any questions for June, we've had some interesting discussion going on in the chat, but I'm sure everyone else is feeling the breakneck speed that I am. We're just more being attentive. We're just being good listeners here. But if anyone has any questions for June, please chuck them in the chat, and I can ask them, and we can get some answers. I just wanted to say though, it's really great, and like you say, June, I know how you sort of prefaced or sort of bookended that with maybe this isn't necessarily required to start stepping into these realms of C++, but I think it's really great to dispel some of the unknown unknowns problem. Like it's like at least if you're
Yeah,
aware of it, you can move forward, and it might not be completely relevant if you're just starting, but that you know it exists. That's great. Like
I really wanted to sort of, and you'll see this also in the later sessions as well, is like dispelling the idea that like there's any magic going on here. It's actually very, if you know the building blocks, if you know how it's actually working under the hood, that it's actually fairly straightforward. Like obviously, yes, it does take time to conceptualize how all of this actually works, but there's nothing magic going on here, right? It is very like straightforward pointers. Everything's memory. You can just use these techniques to get these features, get these high level concepts on a computer that really like everything at the end of the day, everything's just memory and
everything's just a block of
How
memory.
does it work?
Yeah. So people have been like requesting new Redpoint merch, June, for going forward. Everything is a block of memory T-shirts. So there might be some lucrative opportunities there. Just going to say that. Yeah. It looks like we do have a question from Sean. They say it's probably going to be answered in the garbage collection bit, but if you change a pointer which is assigned to a new, I believe that's a constructor invocation object, does the object get removed from memory or leak? Is that something you want to touch on
at the
now?
moment we are not. At the moment we haven't been talking anything. Well, I've made mentions of Unreal specific things, but at the moment, in the context of just normal C++, there's no garbage collection, so you have to call delete on memory that you no longer have, that you no longer want to use. If you assign a pointer to a new and it was currently pointing to something already, unless you call delete on the old thing, it's a memory leak, right? Because it will not. There's no garbage collector. It will not delete it for you because you might have multiple pointers pointing to the same thing, and so you wouldn't want the behavior of, oh, it's going to call delete for me because there might be 2 or 3 or 5 other things referencing it. So the answer is no, it won't do that.
Okay, great. Oh, sorry. Looks like we've got another question. Sorry, I'll just read it out for you. Sorry, this is in the form of this is from a previous session, but if you have something like this, okay, so there's an example here, maybe, of
what I'll do real quick.
Share it.
I'm going to take a screenshot and I will put it up on the thing.
Okay, yeah. So just for a reference point, sorry.
Give me 1 second.
Just for everyone watching the stream,
I've got. Yeah.
One of our very involved question askers is doing cool code snippets in Discord, and
okay, cool. That should be good. Hopefully this is readable. Okay, sorry.
I'll give you the full screen.
Oh, that'd be fantastic. Excellent. Cool. So the question is, if you have something like this, does B get a default constructor because A is trivially constructed, or does having a class always stop a default constructor from being created? That's a good question. Instead of guessing off the top of my head, we're actually just going to write it in Godbolt, and we'll find out. So let's go over to our compiler explorer. And I would recommend that if you are wondering these sorts of things, Godbolt is an excellent tool for finding this stuff out because it will tell you exactly what the compiler is doing. So we look at class A, int num. I believe this will be all trivially copyable all the way down. I need to put my semicolons in. And let's make A B. Oh, I was going to complain at me. Thanks. We need to actually make another copy of B so we can actually see what it's going to do. Yeah, it's all trivially copyable. You'll notice there's no constructors here, so all it's doing is copying some memory straight over. So yeah, this is trivially copyable, which is what I would expect, right? Because I mean, this having only an int inside A makes A trivial, and then because B only contains trivial things, it is also trivial, and then it chains all the way down. Yeah, cool. That's that question done. Right, back.
Yeah, okay, that was great. That's a really good rule. I think. Sorry, and that's another thing I wanted to say. I'm really appreciating about your slides and stuff that you're giving us, June. Is that like how these contain all these like little rules of thumb, right? Like how you just sort of broke that down. It's like, okay, so this class, okay, they are classes, definitions, but they do just literally contain, the primitives there, and just because they're made up of other ones. That's great little things to just keep in mind for everyone. I think, as you sort of parsing all this stuff out. Well, yeah, I think that's it for the questions. I know we are a little bit over time. I guess we'll take a break